Hi, I'm Eric Kai, the Chemical Statistician, and the host of the Central Equilibrium. Today, I will provide a tutorial on naive Bayes classifiers. This tutorial requires prior knowledge of Bayes' theorem. I host a talk show on math, science, and economics called The Central Equilibrium, which covered Bayes' theorem in 2 earlier episodes with my guest Arnab Chakraborty. The first episode was on Bayes' theorem, and the second episode was on the Monty Hall Problem. If you haven't watched those 2 videos yet, then I encourage you to do that first. And I will put the links to those 2 episodes down below in the description of this video. Now, let's talk about naive Bayes classifiers. In statistics and machine learning, naive Bayes classifiers are a supervised learning technique for predicting a categorical target variable, hence the name classifiers. They hinge on a particularly simple but powerful assumption, which is that the predictors are conditionally independent upon a particular value of the target variable. Now that is a rather verbose and an abstract statement, so instead of trying to dive into the theoretical detail, I will illustrate how naive Bayes classifiers work using a simple example, and the theory will become apparent as we go along in the example. Suppose that we're working with a simple data set of 3 variables. The first 2 are the predictors, and the last one is the target variable. Weather can be either sunny or rainy. The functionality of the soccer team's bus is either working or broken down. And the soccer game on that particular day can be either on or off. Now, human intuition would tell us that if the weather is sunny and the bus is working, then the soccer game would likely be on. And conversely, if the weather is rainy and the bus is broken down, then the game is likely to be off. However, I want you to notice that there is no causal relationship or even a deterministic relationship between the 2 predictors and the target variable. Notice for day 2, the weather was rainy, the bus was broken, but the game was still on. And on day 9, the weather was sunny, the bus was working, but the game was off. Therefore, we cannot build a model that is deterministic between the 2 predictors and the target variable. Instead, we need to rely on a probabilistic model. And today, we will use the naive Bayes classifier as that probabilistic model. Now, we can work with the data using the variables as stated in English. However, for mathematical ease, it will be simpler if I convert them into indicator variables. I'm going to use W for weather, B for bus, and G for game. So, I'm going to use 1 for sunny and 0 for rainy. W is then equal to 1, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1. Okay. For the bus, I'm going to use 1 for working and 0 for broken down. So B is equal to 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, and 0. The game status, I will use 1 for on and 0 for off. So G is equal to 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, and 0. So there's our data set expressed in indicator variables. Okay. Now, our goal is to express the status of the game given the weather and the bus's functionality in a probabilistic way. So let's do that using conditional probability. Given the weather and the bus's functionality, what is the probability that the game status is equal to a particular value? So our job is to build a model for this conditional probability. Now, let's suppose that we have a new datum which says that the weather is sunny and the bus is working. So the question is, what can we predict about the game status on that particular day for this new datum? We can answer this question by calculating this probability for the two possible values of G. So we can calculate, first of all, P of G is equal to 1, given W is equal to 1 and B is equal to 1. We will also need to calculate P of G is equal to 0, given W is equal to 1 and B is equal to 1. An intuitive way to answer our question is to compare these two probabilities and see which one is higher. If this probability is higher, then we will predict that the game will be on. If this probability is higher, then we will predict that the game will be off. Now, how do we calculate each of these probabilities? This is where Bayes' theorem comes into play. As I mentioned before, my talk show, The Central Equilibrium, covered Bayes' theorem in 2 previous episodes. If you haven't watched those episodes yet, then I encourage you to do that first, and the links are down below in the description of this video. I will calculate this probability first. We can rewrite this using Bayes' theorem as P of W is equal to 1, B is equal to 1, given G is equal to 1, times P of G is equal to 1, divided by P of W is equal to 1, and B is equal to 1. Now let's calculate the other probability. P of G is equal to 0, given W is equal to 1, and B is equal to 1, is equal to, by Bayes' theorem, P of W is equal to 1, B is equal to 1, given G is equal to 0, times P of G is equal to 0, divided by P of W is equal to 1, and B is equal to 1. Now remember, our goal is to compare these two probabilities, see which one is higher. You can see that these two fractions have the same denominator. Therefore, we do not need to calculate these two denominators to compare these two probabilities. This is really helpful to us because this joint probability can be very difficult to calculate in many applications and in many examples. We have a really simple example here, but in most cases, in most real-life examples, this joint probability is difficult to calculate. So ignoring this is really helpful to us. Now, obviously, I know that this equality is not strictly true, and this equality is not strictly true, but my goal is not to calculate the exact values for these two probabilities. My goal is to compare which one is higher. So we will leave it as written like this. Now, our goal at this stage is to estimate these two probabilities and these two probabilities. And that then allows us to estimate these two probabilities. So I will explicitly put hats on top of these. Now, in most applications, this conditional joint probability is very difficult to calculate. And this is where the naive Bayes classifier comes into play. Up until this point, we have simply used Bayes' theorem. We haven't made any assumptions or used any modeling techniques. So far, we've simply rewritten a conditional probability and ignored a denominator. But now we're going to make a modeling assumption. We're going to assume that these two predictors are independent of each other given this particular value of G. And that right there is that key assumption behind naive Bayes classifiers, that the predictors are independent, conditioned on a particular value of the target variable. Now, you may wonder, is this assumption valid? For this data set, I would actually argue that this assumption is not valid. Let's take a look at the data for which the soccer game is off. Is the weather and the bus's functionality truly independent? I would argue that they are not independent, because if the weather is really bad, if it's really rainy, then perhaps the bus may not work. Perhaps the bad weather could affect the bus's functionality. Maybe the tires are too slippery and cannot grip the pavement when it's moving, and therefore the bus is not safe for transporting the soccer players. So I would argue that the assumption of conditional independence does not apply to my data set. However, and this is a good lesson about naive Bayes classifiers, they often work despite that assumption not working in the scientific background or in terms of the knowledge behind the variables. So even though the assumption does not hold, the probabilistic classifier often still works pretty well in terms of predictive accuracy. So I will go ahead and estimate these probabilities despite thinking that this assumption of conditional independence does not hold, at least for these 5 data points. But I want you to still be aware of this fact that the predictors are not truly conditionally independent, but that this classifier could still work. I want to just also revisit this whole idea of conditional independence in general. So we know that weather and bus functionality are probably not independent if you ignore this conditioning. And the whole point of a naive Bayes classifier is that if you condition it on a particular value of the target variable, that could explain away much of the dependence between the two predictors. And once you explain away that dependence, they become independent, conditioned on that particular value. So that is how the assumption of conditional independence works for naive Bayes classifiers. Again, as I mentioned in this particular data set, I don't think that this is the case, but I think that it's a good approximation to work with to build a probabilistic classifier. Okay, so that's the really theoretical part about this assumption. Let's now actually apply this assumption and estimate these probabilities. So I'm going to say that P of G is equal to 1, condition on W is equal to 1, B is equal to 1. We can estimate this by P of W is equal to 1, conditioned on G is equal to 1, times P of B is equal to 1, conditioned on G is equal to 1, times P of G is equal to 1. Okay. I wrote the word assume here because we're assuming conditional independence. Now, how are we going to estimate these probabilities? Well, this is the easy part because we can just look at the proportions of these variables in which these events are true and substitute for these probabilities. So, for the 6 data points in which the game was on, what's the proportion of the weather that was sunny? And that, as we can see, is 5/6. What about this probability? Out of the 6 data points for which the game was on, there were 4 in which the bus was working. So that's times 4/6. Now, what about this probability? Out of the 11 data points overall, 6 of them had the game as being on. So we're going to multiply by 6/11. This is equal to 120 over 396, which is equal to 0.30 repeated. Okay. Using the same logic, we're going to calculate, we're going to estimate this probability right there. Okay? To be brief, I'm just going to estimate these probabilities from the proportions. This right here, the first probability is P of W is equal to 1, condition on G is equal to 0. So we're looking at the 5 data points where the game was off, and we see that there were 2 days in which the weather was sunny. Now, what about P of B is equal to 1, condition on G is equal to 0? We can estimate that by looking at these 5 data. One of them, the bus was working. So it's 1/5. And lastly, we're going to estimate the probability of P of G is equal to 0. And we have 5 data in which the game was off out of 11 overall. So this is 5/11. And this is equal to 10/275. and this is equal to 0.036 repeated. So this is 0.036363636 onwards. Let's return to our original question. Given this new datum, is the game on or off? And we were going to answer that question by comparing these two probabilities. We estimate these probabilities using the assumption of conditional independence between the two predictors. And our calculations show that this probability is much bigger than this probability. So our prediction is that the game is on. G is equal to 1. And that is how the naive Bayes classifier works. If you enjoyed this video and would like to learn more about statistics or chemistry, or if you'd like to get advice for your career development, I encourage you to read my blog, The Chemical Statistician. If you'd like to watch more video tutorials on statistics or chemistry, please watch more videos on my YouTube channel. If you'd like to watch my talk show on math, science, or economics, which is called The Central Equilibrium, please visit the channel page. And if you'd like to follow me on Twitter, my Twitter handle is @ChemStatEric. And I will put the links to all of those things down below in the description of this video. Thank you for watching this video, and I hope that you learned something useful today.